Okay, let's dive right into this architectural review where we are going to unpack a seriously clever Go program known as Quadchecker. Welcome to the Explainer. Look, if you're a senior developer hunting for a real-world masterclass in clean pipeline architecture and bulletproof defensive programming, you are absolutely in the right place. Today, we're tearing down exactly how this command line app takes piped standard input, analyzes its shape, and dynamically reverse engineers which functions could have possibly rendered it.
So here is our game plan for the teardown. We'll be hitting 1, the overall architecture, 2, the input validation logic, 3, the nested loop renderer, 4, the generator pattern engine, and finally, evaluation and output formatting. We're going to follow the exact chronological data flow of the application today, straight from ingestion to that elegant generator engine.
All right, section 1, the Quadchecker architecture and system execution flow. Let's grab that 50,000-foot view of how data actually moves through this pipeline before we get into the weeds of the code. The whole system executes in 5 very distinct phases. We've got reading the piped standard input, validating the shape's boundaries, dynamically generating candidates, evaluating the matches, and formatting that final console output. What makes this setup so fantastic is how completely decoupled these steps are. I mean, the validation logic doesn't care at all about the matching logic, and the matching logic couldn't care less about how the input was ingested. It is a textbook example of separation of concerns.
Moving on to section 2, and this is a big one, robust input validation logic. We're diving deep into the ingress point to see how the app sanitizes data coming from a pipe, because let's be honest, when you're building a CLI tool, standard input is basically the Wild West. Defending this boundary is absolutely crucial. Using Buffio.scanner, the program efficiently ingests standard input line by line. Now, this is incredibly pipe-friendly because it doesn't try to just dump a massive blob of text into memory all at once. It just appends each line to a string slice. But notice what happens next. It immediately drops in a critical guard clause to halt execution if the input pipe is empty. Literally, if the length of our line slice is 0, it just bails out early and prints not a quad function. That kind of fail-fast methodology is exactly what we want in resilient software.
Once the data is safely ingested, the code calculates the baseline height and width, which sets up our next layer of defense. The height is just the number of rows, the length of the line slice. And the width is simply derived from the length of that very first row. Boom. We now have our target dimensions to test everything else against.
So, what do we actually do with those dimensions? Well, since a valid quad has to be a perfect rectangle, the program iterates through all the rows to ensure their lengths exactly match that initial width we just found. It safely and cleanly rejects any irregular shapes. If row 2 is even one single character shorter than row 1, the program just returns not a quad function. It completely avoids wasting precious compute cycles on malformed data.
All right, section 3, the nested loop renderer and state machine logic. With a perfectly validated rectangle confirmed, we transition to the internal rendering engine. This is where we reconstruct these shapes in memory so we can actually compare them. Notice how the renderer tracks its current location. Right at the heart of it is this neat little micro-narrative, a simple state machine using 4 Boolean flags: is top, is bot, is left, and is right. These pinpoint the exact coordinate type of any cell while we're inside those nested loops. So, instead of dealing with complex, hard-to-read integer math scattered everywhere, we get these super clean, human-readable Boolean states. If we peek at the generate quad A function, we spot another guard clause that returns an empty string for 0 or negative dimensions. This is great because it totally protects our loops from infinite cycling. Right after that, we initialize a string slice to hold our rows. The application then iterates over the height for the outer loop and the width for the inner loop, literally building up the shape one character at a time. And this part brilliantly illustrates the rendering logic. That inner loop uses our Boolean flags inside a highly readable switch statement. It cleanly dictates whether a character should be a corner, an edge, or an interior space. For example, if it's top and left, well, it's a corner. If it's just left, it's an edge. And if none of those flags are true, it just hits the default case and prints an interior space. It's just incredibly elegant. Which brings us to section 4, the generator pattern engine. We are now looking at dynamic evaluation, and I'd argue this is the true architectural centerpiece of the whole application. Instead of hard-coding a bunch of sequential string comparisons, the classic if quad A matches, else if quad B matches nightmare, the developer implemented a generator pattern. By pairing a string identifier with its respective generator function pointer in a single iterative collection, the application achieves a massive boost in scalability.
Looking at the actual Go code, this beautifully concise slice of structs maps strings, like quad A, directly to the generate quad A function pointer. This array holds all 5 rendering algorithms. It allows the whole system to scale up without relying on massive, messy if-else chains. Actually, scratch that, it's even better. If you want to run all the generators, you literally just iterate over this one single slice.
Which leads us perfectly into Section 5, Evaluation and Output Formatting. Let's see how that incoming input pipe finally meets our generated candidates to produce the final match. In just one single elegant loop, the application iterates over that generator array we just talked about. It calls each generator function pointer using the validated dimensions we captured way earlier. And then it directly compares the newly generated string to the original piped input string. If they're a match, it simply appends a quad match struct, which contains the name and dimensions, straight into a matches array. Let's put that into perspective with a real example. Say we have a 5x3 input originating from quad A. The loop executes all 5 functions. It evaluates generate quad A with 5 and 3, finds the exact string match on the very first try, logs it, and then correctly rejects the other candidate strings from quad B through E simply because the resulting strings look entirely different.
To finish up the whole shebang, the program ensures deterministic output by sorting any matches alphabetically before formatting them. This is super critical because, think about it, an input of a 1x1 square actually matches quad C, quad D, and quad E. By using sort.slice, the app guarantees the output is always printed in the exact same alphabetical order, wrapped in brackets and neatly separated by double pipes for the end user. So, the absolutely crucial point I want you to take away as a senior engineer today is this. Consider just how trivial it would be to introduce a brand new shape algorithm, let's call it quadphi, to this pipeline. You'd literally just write the new rendering function and add one single line to that struct slice. The parsing, the validation, the looping, the sorting, none of it would ever need to be touched. And that, right there, leaves us with the true mark of a highly maintainable, brilliantly designed architecture. Thanks for joining me on this explainer. I really hope it gave you some great ideas for your own code bases.